Hi everyone, it's Professor Primton. In this video we're going to talk about models of growth involving differential equations. In the previous video we talked about what a solution to a differential equation might look like, and we also solved separable differential equations. In this video we're going to talk about how to solve differential equations that come up in application problems with exponential growth or decay and also continuous compound interest. So let's pick up where we left off. We're going to talk about models of growth involving differential equations. The population growth rate example that we talked about in the previous video actually demonstrates one basic model of growth, which is proportional to the existing quantity. Bank accounts and populations both tend to grow this way if it's not constrained. This type of growth is called unlimited growth. So unlimited growth, if the quantity or population y grows at a rate proportional to that quantity's size, it can be modeled with unlimited growth, which has this differential equation. Y prime is equal to r times y, where r is a constant. So the y prime is representing the rate of change in a population or a bank account balance. On the right-hand side, you have a constant times the original function, or the balance of the account or the population. So in other words, the population or an account balance will grow at a proportional rate to its size. So example 5, unlimited growth model. Suppose that a bank account grows by 8% each year with an initial deposit of $5,000. Find a function that models the population after t years by solving a differential equation. So we need to set up the differential equation and also solve it. So we know that the bank account balance increases 8% annually, and we also know the initial deposit, which we're going to call capital B for the balance of the account. Capital B of 0 is $5,000. So no time has passed. So t equals 0, the balance is $5,000. And since we're talking about a bank account balance, we know that account balances have unlimited growth. So it must solve this differential equation. Y prime is equal to r times y, where r is a constant. So capital B prime of t is going to be the derivative, so the change in the account balance. We know that r represents the interest rate for this account balance because the account is actually growing each year by 8%. So it's 0.08 times the original account balance, capital B of t. So how fast the bank account balance is growing depends on the interest rate and its original balance. So we need to solve this differential equation. Capital B prime of t will be replaced with y prime, and the b of t will be replaced with y. So that way we have y prime is equal to 0.08 times y. So let's change y prime to be in terms of Leibniz notation. So dy dt on the left-hand side of the equation is equal to 0.08 times y on the right-hand side of the equation. So this is a separable differential equation. Notice that you can multiply both sides of the equation by dt to get dy on one side of the equation is equal to 0.08y times dt on the right side of the equation. So now you can divide both sides of the equation by y to get the dy divided by y on the left-hand side of the equation is equal to 0.08 times dt on the right-hand side of the equation. So everything is in terms of y is on the left-hand side of the equation. Everything in terms of t is on the right-hand side of the equation. So now integrate both sides of the equation. So take the integral of the left-hand side of the equation. So integral dy divided by y, we've seen that before, is equal to the integral of 0.08 times dt. So the left-hand side of the equation, we want to find the family of integers for the function 1 divided by y, dy. So then the family of integers would be natural log absolute value of y is equal to the integral of 0.08 dt. We want to find the family of integers of the function 0.08 when the variable of integration is t. So you get 0.08 times t plus c, the constant of integration. So we want to find out what is the solution to this differential equation. We want to get y by itself. So we've seen this before. Take e and raise it to the left-hand side of the equation. So you get e to the natural log of the absolute value of y on the left-hand side is equal to e to the 0.08 t plus c on the right-hand side of the equation. So e and natural log are inverses of one another. They undo each other. So you get absolute value of y on the left-hand side of the equation is equal to e to the 0.08 times t times e to the c on the right-hand side of the equation. And so e to the capital C, that's just a constant raised to another constant. So that means you just get a constant. So on the left-hand side of the equation, you get absolute value of y is equal to e to the 0.08 times t times some constant of integration, capital C. So just like we did in the previous video, let's find out what is this capital C. We want to find out what is the value of the constant of integration if the initial value, the initial deposit, is $5,000. So if we replace t with 0, the account balance is $5,000. So b of 0 is 5,000. That means you'll get c equals 5,000. So you'll have 5,000 on the left-hand side of the equation is equal to c times e to the 0.08 times 0 in the exponent. And so we know e to the 0 is 1. And so you'll get c times 1 is c, and c is 5,000. So we found out the solution to this differential equation. It must be of the form y equals 5,000 times e to the 0.08 times t. If you've taken college algebra, you've seen this type of function before. 5,000 was the initial deposit for this bank account, and the 0.08 is in the exponent because the account was growing at 8% interest rate annually. And so the solution to this problem was an unlimited growth equation, and it's an exponential function. Whenever a product is advertised heavily, sales will tend to grow very quickly at first, but eventually the market will reach saturation and the sales will actually slow down. In this type of growth, it's called limited growth, and the quantity grows at a rate proportional to the distance from the maximum value. So this is called limited growth. If a quantity grows at a rate proportional to the distance from its maximum value that it attains, capital M, then it can be modeled using a limited growth model, which is satisfying this differential equation. Y prime is equal to some constant k times the quantity, capital M subtract y, the maximum value subtract the function y, where k is a constant and m is the maximum size of the function y. So let's take a look at this next example. Example 6, limited growth model. A new cell phone is introduced and the company estimates that they will sell 200,000 phones. After 1 month, the company has sold 20,000 phones. How many will they have sold after 9 months? So this type of problem will have limited growth because at first the cell phones will be very popular, but then the market will reach saturation and the phone will become less popular. We know that the maximum value of the phones is given in the problem. They will sell 200,000 phones. We also know that when the new phone is introduced, there will be no sales at all. So whenever no time has passed, so whenever t is equal to 0, there will be 0 sales. And they also tell us in the problem that after 1 month, the company will have sold 20,000 phones. Y of 1 is equal to 20,000 phones. And so since this is talking about limited growth, we know that it must satisfy this differential equation. Y prime is equal to some constant k times the quantity, capital M subtract y, where m is the maximum size of the function y. So replacing all the information into this differential equation, we have y prime is equal to some constant k times the quantity, the capital M was 200,000, so just 200, minus y in parentheses. We need to solve this differential equation, which means that we need to find out what is this function y that will make this differential equation true. So again, replace the y prime with dy dt using Leibniz notation is equal to k times 200 minus y in parentheses. Notice that we don't know what the value of k is. K will depend on how popular the phone is. It tells us how fast the phones will actually be sold. However, this differential equation is still a separable differential equation. So that means you can get the function y on the left-hand side of the equation with dy, and on the other side of the equation will be everything not involving y. It will be involving t. So if you divide both sides of this differential equation by 200 minus y, you'll get dy divided by 200 minus y in the denominator is equal to k is on the right-hand side of the equation, and after you multiply the right side of the equation by dt, you'll get k times dt. And so the left-hand side of the equation is involving a function of y, and on the right-hand side of the equation you have a constant, and the function will be in terms of t. So now that we have the differential equation separated, we can integrate both sides of the differential equation. So take the integral on the left-hand side of the equation, 1 divided by 200 minus y dy is equal to the indefinite integral on the right-hand side, k dt. So notice on the left-hand side, we don't have 1 divided by y, we have 1 divided by a function of y. So we need to use substitution method to find out the family of integers. So let's let u be 200 minus y, the denominator of this fraction. So we know that we need to take the derivative of u. The derivative of 200 is 0, and the derivative of negative y is negative 1 dy. So du is negative dy, or dy is negative du if you divide both sides of this equation by negative 1. So going back to this integral, you have the integral of 1 divided by 200 minus y, that's being replaced with a u. So you have the indefinite integral of 1 divided by u. The dy is replaced with negative du. So 1 divided by u, negative du. So on the right-hand side of the equation, notice you don't have to use the substitution method because it's just a constant. We can find the family of integers of just the constant. So on the left-hand side of this equation, you have the integral. The negative can be taken outside the integral sign, so you have 1 divided by u, du left. And on the right-hand side of the equation, you have the integral of k dt. So what is the antiderivative of 1 divided by u with respect to u? It's the natural log of the absolute value of u. So you have negative on the outside that you need to keep. Natural log of the absolute value of u is equal to the family of integeratives of just the constant k, where the variable integration is t. It's k times t. So k times t plus c, where c is the constant of integration. So just like the last example, we want to find out what is the function that satisfies this differential equation. So let's divide both sides of the equation by negative 1 to get this natural log of absolute value of u by itself. So natural log absolute value of u is equal to kt divided by negative 1 will be negative k times t. plus the constant divided by -1 will just be another constant, so just plus c again. Now with the substitution method, we know that we need to replace the u with what we said the inside function was. We called it 200 minus y. So we have natural log of the absolute value, 200 minus y, is equal to the right-hand side of the equation, negative k times t plus c. So again, just like all the other examples, we need to get y by itself, and y is inside the natural logarithm here. So we want to raise e to the left-hand side of the equation as a power, and also do the same thing on the right-hand side of the equation, e to the negative kt plus c on the right-hand side. E and natural log are inverses of one another, so you'll just be left with 200 minus y on the left-hand side of the equation is equal to, and on the right-hand side of the equation you have e to negative kt plus c. We know that we can rewrite this as a product of two different exponential expressions. We have negative e to negative kt times e to the c. And e to the c is just a number that's raised to another real number, so you'll just get a constant. So it's just negative c e to the negative kt. And so now we can get y by itself. We can subtract both sides of the equation by 200 and then also divide by -1. So you'll come up with y is equal to capital C, the constant of integration, e to the negative kt power plus 200. Now we can use information in the problem to help us find out what is the value of c. So since the initial value, the number of cells of the phone was 0, y of 0 was 0. So if you plug in 0 for the t, the value of y will be 0, and we can use that to find c. So the function was y equals capital C e to negative k times t, well t is being replaced with a 0 now, plus 200 is equal to the y value is being replaced with a 0. So you have c times e to the 0 power plus 200, that's all equal to 0. And so c times 1 plus 200 equals 0, and so that means capital C will be negative 200 after you solve for capital C. And now we can find out the value of k. So now we can use the information about how many sales were after 1 month for the phone. After 1 month, there were 20,000 phones sold. So if you replace the t with a 1, the y values will be 20. Use this to find the value of k. So y is equal to, the c is replaced with negative 200, so negative 200 times e to negative k times t, well t is replaced with a 1, plus 200 is equal to, the y value is 20. So now we can solve for k. So subtract 200 on both sides of the equation first to get the exponential expression by itself. So you have negative 200 e to negative k power is equal to negative 180. Now if you want to solve for k and k is in the exponent, we need to actually take natural log, but not yet. We need to get e to the negative k by itself. So divide both sides of the equation by negative 200 first. So you get e to negative k on the left-hand side of the equation by itself. Negative 180 divided by negative 200 will be positive 180 divided by 200, or just 0.9. And now you're ready to take the natural log on both sides of the equation. So natural log of the left-hand side of the equation, so natural log of e to negative k is equal to natural log of 0.9. And so again, natural log and base e are inverses of one another. They'll just cancel each other out, and you'll be left with negative k on one side of the equation is equal to natural log of 0.9. And so divide both sides of the equation by -1 to get k by itself. And so k is negative natural log of 0.9, which will come out to be 0.105. So after 9 months, the number of phones sold will be y is equal to negative 200 for the c is equal to e to the negative 0.105, that was the k. T is 9 for 9 months plus 200. And if you calculate this, you'll come up with y is approximately 122.26 if you round the two decimal places, and y was in thousands of phones sold. So about 122.26 thousand phones sold in the first 9 months. Limited growth is also commonly used for learning models, since when learning a new skill, people typically learn quickly at first, and then their rate of improvement for learning slows down as they approach mastery. So example 7, limited growth model. Jim is learning a new set of product codes for work. Each day, Jim studies and tests recall. Suppose that after 4 days, Jim has mastered 70% of the new codes. How long will it take for Jim to master 95% of the codes if the limited growth model applies to this situation? So there's a lot of information given in the problem. But notice in the problem, the maximum mastery that Jim can attain is 100%. That's when Jim learns every single code that he was presented. So n will be 100%, or just 100, and it must satisfy the differential equation for limited growth model. Y prime is equal to lowercase k times the quantity, capital M minus y. And so you can replace the m with 100. So y prime is k times the quantity, 100 minus y. So just like the last example, we have a couple pieces of information that we can use. After 4 days, so whenever t is 4, Jim has mastered 70%. So y of 4 is 70. And also assuming that Jim didn't learn any codes at first, so no time has passed, Jim learned 0% of the codes. So y of 0 is 0. So let's start off by solving the differential equation first. So y prime will be replaced with dy dt again, equals k times the quantity 100 minus y. So let's solve this exactly like we did in example 6. So with this differential equation, start off by multiplying both sides of the equation by dt, so that way you have dy on one side of the equation by itself is equal to k times the quantity 100 minus y times dt. Divide both sides of the equation by 100 minus y so that the function y is on the left-hand side with dy, and the k is on the right-hand side with dt. So you have dy divided by 100 minus y is equal to k times dt, and so the function y is on the left-hand side of the equation with dy, and k is on the right-hand side of the equation with dt. So now integrate both sides of the equation. So take the indefinite integral on the left-hand side of the equation. So indefinite integral of 1 divided by 100 minus y dy is equal to the indefinite integral of k, the constant k, times dt. So we've seen this before. We have not just 1 divided by y, we have 1 divided by a function of y. So let's use the substitution method. Let u equal 100 minus y, the denominator of this fraction. And so now the derivative of u would be du is equal to, the derivative of 100 is 0, and the derivative of negative y is negative dy. So du is negative dy, or dy is negative du. So the left-hand side of this equation will be 1 divided by u, and the dy is replaced with negative du. So integral 1 divided by u, negative du, is equal to the integral on the right-hand side of the equation, integral of k dt. And so the family of integratives of the left-hand side of the equation would be negative natural log absolute value of u is equal to the family of integratives on the right-hand side of the equation would be k times t, because the variable integration is t again, plus c. And then the last step for the substitution method is always to go back and replace the u as the inside function. The u was 100 minus y, so you have negative natural log of the absolute value of 100 minus y is equal to k times t plus c. And again, we want to be able to solve this equation for y, so we can find out what is the function that satisfies the differential equation. So take e and raise to the left-hand side of the equation. So you have e to the natural log absolute value of 100 minus y is equal to, after you divide both sides of the equation by negative 1, you'll have e to negative kt plus c again. And so the right-hand side of the equation, you have a sum in the exponent. That means you have a product of the exponential expressions. So you have e to negative kt times another constant. That's capital C e to negative kt. And so after e and natural log undo each other because they're inverses, you'll just have 100 minus y left over on the left-hand side of the equation equals capital C times e to negative kt. And so now we want to find out what is the function y, so solve this equation for y. Subtract 100 on both sides of the equation and then divide both sides of the equation by negative 1. You'll come up with y is equal to capital C times e to negative kt power plus 100. And so now the rest of the problem is going to work just like we did in the last example. We want to find out what is the value of c first, and then we can find out the value of k, and then we can answer the question that's actually posed in the problem. So now that we know what the function is, y is equal to c times e to the negative kt power plus 100. If we plug in 0 for the value of t, we know that Jim has 0 codes memorized after 0 days. So 0 is equal to capital C e to the negative k times 0 plus 100. And so that will be e to the 0 power, which is 1. C times 1 is just c. And so c plus 100 is equal to 0. That gives you capital C is negative 100. And so now that we've found out what the capital C is, now we can find the value of k. Use the information now for y of 4 is equal to 70 to find the value of k. So y is equal to c, well, we found out that's negative 100, so negative 100 e. So now t is replaced with a 4, so you have negative k times 4, plus 100 is equal to the y value is 70. 70% of the codes will be mastered after 4 days. And so now we need to solve this equation for k, and k is in the exponent. So let's get the exponential expression by itself first. So subtract both sides of the equation by 100. So you get negative 100 e to negative 4 times k is equal to negative 30, because you'll have 70 to subtract 100 on the right-hand side of the equation. Before you take the natural log, you need to get e to negative 4k by itself. So divide both sides of the equation by negative 100. So you have e to negative 4k by itself on the left-hand side of the equation. On the right-hand side of the equation, you'll have negative 30 divided by negative 100, or positive 30 divided by 100, or 0.3. So e to negative 4k is equal to 0.3. So now take the natural log on both sides of the equation so that you can get k by itself. So you'll have natural log of e to negative 4k is equal to natural log of 0.3 on the other side of the equation. The natural log and e are inverses of one another, so you'll be left off with negative 4 times k is equal to natural log of 0.3. So now if you want to get k by itself, divide both sides of the equation by negative 4. And so k is equal to natural log 0.3, get that answer, and then divide by negative 4. And you'll come up with about 0.301. So now that we found out the value of k, and we know what the value of c is, and we know the function y, we can actually answer the question that was posed in the problem. How long will it take Jim to master 95% of the codes for the limited growth model? So since mastery is at 95%, that's the value of y. So solve the equation y is equal to 95. So you have the left-hand side of the equation is 95 replacing the y equals the right-hand side of the equation is negative 100, that's the value of c, e to negative 0.301, the k was 0.301 times t in the exponent plus 100. So you need to first subtract 100 on both sides of the equation. So 95 subtract 100 gives you negative 5 is equal to negative 100 e to negative 0.301 t. Divide both sides of the equation by negative 100 to get the exponential expression by itself. So you get negative 5 divided by negative 100, that's 0.05 e to the negative 0.301 t. And so now take natural log on both sides of the equation. So you have natural log of 0.05 is equal to natural log of the right-hand side of the equation. So e to the negative 0.301 t. Natural log and e are inverses one another, so you'll just be left off with negative 0.301 t on the right-hand side of the equation. So to get t by itself, divide by negative 0.301, and so t is natural log 0.05 divided by negative 0.301. If you put this in the calculator, you'll get approximately 9.95. And since this is talking about days, we want to round to the nearest day, so about 10 days. It will take Jim about 10 days to master 95% of the codes. So let's finish up this video talking about one more type of growth model. Earlier we talked about unlimited growth to model a population. However, population will be constrained by food, space, and other resources. When a population grows, both proportional to its size and also relative to the distance from some maximum value, then we have what's called logistic growth, and it will be called a logistic growth model. This leads to a differential equation of this form. Y prime is equal to k times y times the quantity capital M minus y, which is far more accurate than what we had before. But it's not always convenient to use because the function's a little bit more complicated. We're going to use a slight modification to solve differential equations of this form that requires integration techniques that we have not learned, and so a solution form is given. So logistic growth. If a quantity grows at a rate proportional to its size and to the distance from the maximum value capital M, it can be modeled by logistic growth, which satisfies this differential equation. Y prime is equal to r times y, or k times y, times the quantity 1 minus y divided by m, where r can be interpreted as the growth rate absent constraints, how the population would grow if there was no maximum value. This differential equation has the solution of this form. Y is equal to capital M divided by the quantity 1 plus a e to negative rt. So the solution to this differential equation is of this form. We don't actually have to solve a differential equation anymore. It's going to be of this form for logistic growth. So let's do one more example. Example 8, logistic growth model. A colony of 100 rabbits is introduced to a reclaimed forest. After 1 year, the population has grown to 300 rabbits. It is estimated the forest can sustain 5,000 rabbits. If the Forest Service plans to reintroduce wolves to the forest when the rabbit population reaches 3,000, determine the number of years before this will occur. So notice in the solution to the differential equation, we need to know what the maximum value is. The maximum sustainable population in this forest was 5,000 rabbits. So capital M is 5,000. So since the population can be modeled using this logistic growth model, capital M divided by 1 plus a e to negative rt, then the 5,000 is replaced with the m. So m is replaced with 5,000. So you have 5,000 divided by 1 plus capital A e to negative rt. So just like before, we have information that was presented in the problem that can help us find out the values of both a and also r. So we need to have two pieces of information because we have two different unknown constants. We want to find out what is the value of a first, and then we'll find out the value of r next. So use the information that the initial population of the rabbits that was introduced into this forest was 100. So no time has passed, so t equals 0, and the population was 100. So if you replace the y with 100, you have 100 is equal to 5,000 divided by 1 plus capital A e to negative r times t. Well, t is replaced with a 0, so negative r times 0 in the exponent. That's 5,000 divided by 1 plus capital A e to the 0 power. E to the 0 is 1, so the denominator just becomes 1 plus a times 1, and so that's just 1 plus a. So 5,000 divided by 1 plus a is equal to 100. We need to solve this equation for a. So this is called a rational equation because the variable is in the denominator of this equation. And so if you multiply both sides of the equation by the denominator, you'll clear the denominators, and so you don't have any fractions anymore. So 100 times 1 plus a on the left-hand side of the equation is equal to 5,000 divided by 1 plus a times 1 plus a, so the 1 plus a's will cancel out, and you'll just be left with 5,000. So now solve for a. Distribute the 100 through the parentheses to remove the parentheses. So 100 times 100, 100 times a, 100a is equal to 5,000. Solve for a, so subtract 100 on both sides of the equation. So 100 times a is equal to 4,900, or a is equal to 49 after you divide both sides of the equation by 100. So we found out the unknown constant a. Now let's use the information that after 1 year, the population of the rabbits were 300 in the forest. So after 1 year, so when t is equal to 1, the population y is equal to 300. So go back to the equation for the solution to the logistic growth model. 300 is going to replace the value of y, the population of the rabbits, is equal to 5,000 was the maximum value for the population, divided by 1 plus, we found out a already, that was 49, e to negative r times t, well t is replaced with 1. So the right-hand side of the equation becomes 5,000 divided by 1 plus 49 e to negative r power. So notice again that we want to solve for the variable r, but r is located in an exponent. So we need to multiply both sides of the equation by the denominator to clear denominators. So we have 300 times the denominator, so 300 times 1 plus 49 e to negative r in parentheses is equal to 5,000 divided by 1 plus 49 e to negative r times itself. So you have 5,000 on the right-hand side of the equation after the denominators cancel out. Divide both sides of the equation by 300, so you have 1 plus 49 e to negative r power is equal to 5,000 divided by 300, simplifies to 50 divided by 3. Subtract 1 on both sides of the equation so you can get the exponential expression by itself first before you take natural log. So subtract 1, you have 49 e to negative r is equal to 50 divided by 3, subtract 1 would be 47 thirds. Now divide both sides of the equation by 49, so you get e to negative r by itself. So e to negative r is equal to 47 thirds divided by 49, which will be approximately 0.3197. So e to negative r is equal to about 0.3197. We want to use natural logarithm again to help us cancel out the base e. So natural log of e to the negative r power will be natural log of the right-hand side of the equation, natural log of 0.3197. And so natural log and e are inverses of each other. You'll just be left off with negative r is equal to natural log of 0.3197. And then divide both sides of the equation by negative 1, and you'll come up with r is about 1.1404. So now that we found out the constant a, and we also found out the constant r, we can go back and figure out what is the solution to the differential equation that models the logistic growth of the population of rabbits in the forest. Y is equal to m was 5,000, divided by 1 plus a, we found a was 49, e to negative rt power, r was 1.1404, so you'll have e to negative 1.1404 times t in the denominator. And now to answer the question that was posed in the problem, the Forest Service will introduce wolves into the population once the rabbits have reached 3,000. We want to find out when is this population that's modeling logistic growth going to reach 3,000. So when is y 3,000? Replace the y with 3,000. So again, we have to solve for t this time because we want to find out how much time has passed before the population reaches 3,000. So we have 3,000 is equal to 5,000 divided by 1 plus 49 e to negative 1.1404 t. So again, t is the variable that we want to solve for, and it's in the denominator of this fraction. So multiply both sides of the equation by the denominator to clear denominators. So you have 3,000 times 1 plus 49 e to negative 1.1404 t is equal to 5,000. Divide both sides of the equation by 3,000 first. So you have 1 plus 49 e to negative 1.1404 t is equal to 5,000 divided by 3,000. It just simplifies to 5 thirds. Subtract 1 on both sides of the equation so you can isolate the exponential expression by itself. So you have 49 e to negative 1.1404 t is equal to 5 thirds. Subtract 1 is 2 thirds. And now divide both sides of the equation by 49 to get e to the power by itself. So e to negative 1.1404 t equals 2 thirds divided by 49, which is approximately 0.01361. And now you have e to a power by itself on one side of the equation. You can use the natural log to help you cancel out base e. So natural log of e to the exponent negative 1.1404 t is equal to natural log of 0.01361. And so natural log and base e will undo each other because they're inverses. You'll be left off with negative 1.1404 t is equal to natural log of 0.01361. And now divide both sides of the equation to get t by itself. So t is natural log 0.01361 divided by negative 1.1404. And that will be approximately, when you put this in the calculator, 3.77. Now we don't want to round this answer because this is talking about years. So you'll take the population of the rabbits to reach 3,000 about 3.77 years after the rabbits were introduced to this forest. And the last thing to note is that logistic growth is also a good model for unadvertised sales. A new product that is not advertised will have sales that increase slowly at first, but then will grow as the word of mouth spreads and people will become more familiar with the product. Sales will level off as they approach market saturation. So this finishes our video on growth as a model involving differential equations. If you have any questions about any examples in this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you at the next video when we talk about Riemann sums and approximating rectangles for area under a curve.